In this lesson, we will delve into task 3.1 of Project 3, which involves the design of the drilling and boring process plan and the analysis of typical cases, specifically focusing on the formulation of the hole machining process route. In metal cutting processes, hole machining is an extremely important aspect. A well-devised hole machining process route can ensure the quality of the hole and improve production efficiency. We will learn about the relevant concepts, methods, and practical applications of formulating hole machining process routes, and we will also deepen our understanding through case analysis. In the field of metal cutting, hole machining is a common and critical operation. Task 3.1 focuses on the formulation of the hole machining process route, which is essential for ensuring machining accuracy, surface quality, and improving production efficiency. Basic concepts of formulating hole machining process routes. The hole machining process route refers to the combination of machining methods and sequences used throughout the entire process from raw material to finished hole. A well-designed process route can fully utilize the performance of machine tools and cutting tools, reduce machining errors, and improve production efficiency. When formulating a hole machining process route, multiple factors need to be considered comprehensively, such as the workpiece material, hole dimensional accuracy, surface roughness requirements, and the production volume. Common hole machining methods. Drilling. Drilling is a fundamental method of hole machining, typically performed on a drilling machine, but it can also be done on a lathe. The accuracy of drilling is relatively low, with general dimensional accuracy ranging from IT11 to IT13, and surface roughness RA between 12.5 and 50 micrometers. The principle of drilling involves the rotation and axial feed of the drill bit to create a hole in the workpiece. There are many types of drill bits, with twist drills and center drills being the most common. The twist drill is the most widely used drill bit, consisting of a shank, neck, and a working part. The working part is further divided into the cutting part and the guiding part. The cutting part is responsible for the main cutting work, while the guiding part ensures the correct feed direction of the drill bit. Hole expanding. Hole expanding is a method used to enlarge an existing hole. It can improve the dimensional accuracy and surface quality of the hole, with general dimensional accuracy reaching IT10 to IT12 and surface roughness RA between 3.2 and 6.3 micrometers. The tool used for hole expanding is a core drill. The core drill has more teeth than a twist drill, usually 3 to 4, so it has good guidance and stable cutting. Reaming. Reaming is a finishing method used to improve the dimensional accuracy and the surface quality of a hole. The dimensional accuracy of reaming can reach IT7 to IT9, with surface roughness RA between 0.8 and 1.6 micrometers. The tool used for reaming is a reamer, which is divided into hand reamers and machine reamers. Hand reamers have a longer working part and provide good guidance, making them suitable for manual reaming, while machine reamers are used for reaming on machine tools. Reamers have a higher number of teeth, generally 6 to 12, with sharp cutting edges that ensure the accuracy and surface quality of the reamed hole. Boring. Boring is a commonly used hole machining method that can be performed on boring machines, lathes, milling machines, and other machine tools. It is capable of machining holes of various sizes and accuracies, and is particularly suitable for large diameter holes and hole systems with high positional accuracy requirements. The dimensional accuracy of boring can reach IT7 to IT9, with surface roughness RA between 0.8 and 1.6 micrometers. The tool used for boring is a boring tool, which can be either a single-edged or double-edged boring tool. Single-edged boring tools have a simple structure and are easy to manufacture, allowing for adjustments based on machining requirements, but they have lower cutting efficiency. Double-edged boring tools offer higher cutting efficiency, but their manufacturing and adjustment are relatively more complex. Principles for formulating hole machining process routes. Ensuring machining accuracy. When formulating a hole machining process route, it is important to select appropriate machining methods and sequences based on the requirements for dimensional accuracy, shape accuracy, and positional accuracy of the hole. Generally, rough machining is performed first to remove most of the excess material, followed by semi-finishing and finishing to gradually improve the accuracy of the hole, improving production efficiency. The machining sequence should be arranged reasonably to reduce machine adjustment time and the number of tool changes. For example, using composite tools or multi-tool machining methods to process multiple holes simultaneously can enhance production efficiency, reducing machining costs, while meeting the requirements for machining accuracy and production efficiency. It is important to choose cost-effective machining methods and tools. For instance, drilling can be used for holes with lower accuracy requirements, while a process route of drilling, reaming, finishing can be employed for holes with higher accuracy demands. Typical case analysis. Suppose we need to machine a hole with a diameter of 530H7 and a surface roughness Ra of 1.6 micrometers. The workpiece material is 45 steel, and the production volume is medium batch. Let's formulate the machining process route for this hole. Analyze the machining requirements based on the dimensional accuracy of the hole. Analyzing machining requirements based on the requirements for the hole's dimensional accuracy of 530H7 and surface roughness Ra of 1.6 micrometers. We can determine that the hole requires finishing. Selection of machining method. Given the high accuracy requirements for this hole, we can adopt a process route of drilling, reaming, finishing. The specific steps are as follows. Drilling. Use a twist drill with a diameter of 528 to perform drilling on a drilling machine. The dimensional accuracy of drilling is relatively low, but it can remove most of the excess material. Reaming. Use a reamer with a diameter of 529.8 to perform reaming on a drilling machine. Reaming can improve the dimensional accuracy and the surface quality of the hole. Boring. Use a reamer with a diameter of 530H7 to perform boring on a drilling machine. Boring can achieve the final dimensional accuracy and surface roughness requirements. Determine the machining sequence. Following the principle of roughing before finishing, start with drilling, then proceed to reaming, and finally perform finishing. During the machining process, attention must be paid to the selection of tools and the adjustment of cutting parameters to ensure machining quality and production efficiency. Integration of ideological and political elements. When developing a comprehensive hole machining process specification, we must emphasize the interconnection and systematic nature of each process step. Just like a team completing a complex task, each process has its unique role, and they work together and influence each other. This requires us to cultivate the ability to think from a global perspective, rather than focusing solely on a single process while neglecting the whole. Additionally, in actual production, a sense of standardization and team collaboration is crucial. Standardized operating procedures can ensure machining quality and production safety, while collaboration among team members can enhance production efficiency and collectively accomplish production tasks. In this lesson, we focused on Task 3.1 from Project 3, which involves the design of drilling and boring process plans and the analysis of typical cases, specifically the formulation of hole machining process routes. We learned the basic concepts of hole machining process routes and mastered common hole machining methods, including the characteristics and the applicable scopes of drilling, reaming, finishing, and boring. We also studied the principles for formulating hole machining process routes, which are to ensure machining accuracy, improve production efficiency, and reduce machining costs. Through the analysis of typical cases, we further grasped how to formulate a reasonable hole machining process route based on specific machining requirements. Additionally, We emphasize the importance of a systems engineering perspective and professional competence. I hope that in your future studies and work, you will develop the ability to think from a global perspective, establish a sense of standardization, and emphasize teamwork.